So we will use the results of the previous lecture to prove theorem Seifert-Van Kampen. Let X be a path-connected topological space let U and V be path-connected open sets such that U intersection V is path-connected. Let X naught in U intersection V be a point. Then we have maps induced by the inclusions pi 1 U intersection V X naught to pi 1 U X naught and pi 1 U intersection V X naught to pi 1 V X naught. Then pi 1 X X naught is isomorphic to so let's denote these maps by I1, I2, the amalgamated product. So let's see a proof. The proof is long and it is done in several steps. So the inclusions U into X and V into X induce maps. So we'll denote them by J1 from pi 1 U X naught to pi 1 X X naught and J2 from pi 1 P X naught to pi 1 X X naught. And we have a commutative diagram pi 1 U intersection V X naught So suppose we are given another triple H and maps phi 1 and phi 2 such that, suppose we are given such that phi 1 compose J1, I1, sorry, is equal to phi 2 compose I2. Then we will show that there is a unique map psi from pi 1 xx naught to h, which makes the diagram commute. Then by the last proposition, in the previous lecture, it follows that pi 1 xx naught is the amalgamated product. So the uniqueness of psi is clear in view of the exercise, which asked to show that pi 1 xx naught is generated by the subgroups J1 pi 1 ux naught and J2 pi 1 vx naught. So it only remains to prove that psi exists. So let us prove that psi exists. So we need a definition which we have already seen implicitly, but let's just make it explicit. Let Y be a topological space and let F from 0, 1 to Y be a path. So F is a path from A to B. So let G be another path from A to B. From A to B. So we say F is homotopic to G in Y if there is a homotopy from I cross I to Y. So it leaves the ends fixed, and here it is F and here it is G. So as we saw before, using the same ideas, it is easily checked that tilde y is an equivalence relation. On the space of parts. And if f1 is homotopic to g1 and f2 is homotopic to g2, then f1 star f2 is homotopic to g1 star g2. Well, we also need and f1 of 1 is equal to f2 of 0. So here we have f1, here we have f2. So the endpoint of f1 is the same as the starting point of f2. And here we have g1 and g2. So then the concatenated loops are also homotopic. So the homotopy class, now we return to our situation of x, u and v of a path f in u, v, x will, so if f is in u, v or x, will be denoted by, or u intersection v also, will be denoted by fu, fv. So we will drop the x, but for other sets we will indicate respectively. So our aim is to define a map psi from pi1 xx0 to h such that psi compose ji is equal to phi I. So step 1, so let L u x0 denote the space of loops at x0 and contained inside u. So these loops are completely contained inside u. Similarly, we have L v x0. So both these are subspaces of L xx0. So we first define a map rho of sets from LU x0 union LV x0 to H by rho of F is defined to be phi 1 of fu if f is in u, or phi 2 of fv if f is in v. So when f is in u intersection v, then the condition so then we may write fu is equal to I1 of fu intersection v, and fv is equal to I2 of fu intersection v, and the condition phi 1 compose I1 is equal to phi 2 compose I2 shows that rho is well defined. So let us observe that rho satisfies the following conditions. All of which are obvious from the definition. So let's write these on the next page. If fu is equal to gu, then rho f is equal to rho g. If both f and g are in u, then rho of f star g is equal to rho of f times rho of g. And so let me just write same for v. If both f and g are in v, then again rho of f star g is equal to rho of f times rho of g. So let's come to step 2. So we extend the definition from loops contained in u or v and based at x0 to paths contained in u or v. Denote the set of all paths in u by p of u. Similarly, we have p of v So again, both these P of u and P of v are subsets of P of x, and we want to define sigma from P of u union P of v to h, which extends rho. So before we define sigma, first we will fix some choices. For each x in x, fix once and for all the path alpha from x0 to x. But we choose the paths alpha x subject to some conditions. So choose alpha x. So if x equal to x0, then let alpha x0 be the constant path. Cx0. If x is in u, v, or u intersection v, since all these are path connected, choose alpha x to be contained in u, v, or u intersection v. So we will define sigma using the paths alpha x. So let gamma be a path which is completely contained inside u or v. So gamma is a path from x1 to x2 and is completely contained inside u or v. Here we have alpha x0, sorry, alpha x1. Here we have alpha x2. So we define. So suppose gamma is contained completely inside u, then alpha x1 also is going to be completely contained inside u by our choice, and alpha x2 is also completely contained inside u. So we define sigma of gamma to be equal to rho of alpha x1 star gamma star the inverse of alpha x2. So this is the inverse of alpha x2. So if gamma is a loop, so before that, clearly this is a loop at x0 contained in U or V. And so this makes sense. And we need to show that sigma extends rho. So if gamma is a loop in U or V based at x0, then since alpha x0 and C, since alpha x0 is the constant loop, so alpha x0 star gamma star I alpha x0 rho of this thing is by definition phi 1, let's say it's contained in U, this is equal to phi 1. So thus sigma extends rho. So it satisfies also sigma satisfies the following two properties. For paths F and G contained in U or V, the first is F is homotopic to G inside U, then sigma F is equal to sigma G. This is clear because so we have F is homotopic to G, this x1, this x2. Because then we will have alpha x1 star F star I alpha x2 plus U is equal to the homotopy classes are the same. And rho only depends on the homotopy class. So the second property we need to check is, which is holds, is those F and G, both of them are contained in U. There's x1, x2 and x3. Then sigma of F star G is equal to sigma F times sigma G. So once again, this is easily checked from the definition because rho satisfies a similar property for loops based on. So let me just write both these are easily checked using the definition. So similar properties. So using the definition, and properties of rho. So similar assertions hold for f and g contained in V. So next we come to step 3. So we want to extend sigma to a map tau from all paths in X to H. So let f be a path in X by the Lebesgue number lemma we can partition the interval zero one. So 0 S1 Sn minus 1, this Sn, such that so Sn is equal to 1, this S0, f of Si comma Si plus 1 is contained inside U or V. So we define Fi from 0 1 to Si plus 1. This is simply let me just say take a linear map, or let's say affine. So basically we translate and scale, or we scale and translate, and this is F. And then F is homotopic to this obvious. So where each Fi is in P of U union P of V. So zero, so this is F1, this is F2, and so on. So define tau of F to be equal to sigma of F0 dot sigma of F1 dot sigma of Fn minus 1. So this, of course, depends on the partition, and we need to show that tau of F is independent of the partition chosen. So let's try to do that. So let P be a partition of 0 1 and consider P union a point C. So our P is the partition like this, and let's say here we have some Fi, and P union C, we just add one point C in the middle of Si and Si plus 1, let's say, So, and let's say we have this GA. So tau f using the partition P is sigma f naught dot sigma f1 dot sigma fn, and tau f using the partition P union C is equal to sigma f naught dot sigma f1 goes on up to sigma fi minus 1. Then we get sigma of g times sigma of h, and then sigma of fi plus 1 up to sigma of fn minus 1. But as sigma of fi is equal to sigma of g star h equal to sigma of g times sigma of h using the properties of sigma. So this implies that tau of f comma p is equal to tau of f comma p union c. And we can do this for finitely many points. So thus, for any partition, for any two partitions, p and p prime, we get tau f comma p is equal to tau f comma p union p prime is equal to tau f comma p prime. So thus, tau is well defined. Next we come to step 4. Show that, in this step we will show that if f is homotopic to g, so this is in x, then tau f is equal to tau g. So we will do this in 2 steps. So let f be a homotopy from f to g. So it keeps the ends fixed all the time. So we first consider a special case. So we assume that there is a partition of 0, 1 such that for each I, f of si comma si plus 1 cross I is contained in U or V. So in terms of a diagram, this is Si, these are F to X, this is Si comma 0, Si plus 1 comma 0, Si comma 1, Si plus 1 comma 1, and this is Fi, this beta I, let's call this path beta I plus 1, and this is our Gi. So for each I, we have that the assumption is that the image of this rectangle is contained in either U or V. So beta I is the path f of si comma t and beta I plus 1 is the path of si plus 1 comma t. So let us assume that f of si plus 1 cross I is contained inside U. So then it is clear that fi star beta I plus 1 is homotopic inside U to gi star beta I. From this we get that sigma of fi times sigma of beta I plus 1 is equal to sigma of gi. Oh, sorry, I wrote this incorrectly. Is beta I star gi. Times sigma of gi, which implies that sigma of fi is equal to sigma of beta I, sigma of gi, sigma of beta I plus 1 inverse. Thus, tau of f is by definition sigma of f0, sigma of f1, and so on, up to sigma of fn minus 1. This is equal to product I equal to 0 to n minus 1, sigma of beta I, sigma of gi, sigma of beta I plus 1 inverse. This is equal to sigma of beta 0, sigma of g0, sigma of g1, sigma of gn minus 1, sigma of beta n. Now beta 0 and beta n are constant paths by the definition of homotopy. So thus sigma beta 0 is equal to sigma beta n is the identity, and thus it follows that tau of f is equal to sigma of g0 to sigma of g n minus 1, which is equal to tau of g. So now we do the general case. So here we have a homotopy from f to g. So again, by Lebesgue number lemma, we can break the homotopy into pieces. So by using break the homotopy into rectangles such that each rectangle is contained in U or V. So let's say this is T0, this point is T1, this point is T2, and so on. So let Hj of S denote the path f of S comma Tj. Then this region then the homotopy between each Hj and Hj plus 1 satisfies the condition in the special case. Thus, tau of Hj is equal to tau of Hj plus 1, and this implies that tau of f is equal to tau of H0 is equal to tau of Hm is equal to tau of G. So this completes the proof of step 4. So now let's go to step 5. For f and g, which are parts in X, tau of f star g is equal to tau of f times tau of g. So f star g, we can choose a partition like this, f0, f1, and so on, up to g0, g1, and so on. So each fi and gj is contained in U or V. Then by definition, tau of f star g is equal to tau of f naught, sigma of f naught, sigma of f1, and so on, sigma of f n minus 1, and then sigma of g0 up to sigma of gm minus 1, let's say. And this is equal to tau of f times tau of g. So step 6. So we restrict tau to L xx naught. So we have the inclusion is a subset of p of x. We have defined tau to h, and because of step 4, tau factors through, so the restriction factors through pi 1 XX0 by step 4. Psi is a group homomorphism by step 5, and from the definition, so the first, in step 1 we use the notation rho since tau restricted to L, U is equal to rho. From the definition of rho, it follows that psi compose Ji is equal to phi I. So this completes the proof of the theorem. So we will stop here.